Mr. Chairman, whenever you want.
Actually, we are set. Go ahead. Thanks a lot.
Okay, so good morning, everybody. I'm starting this workshop with a general presentation of the VESPA activity, which is actually in this
Sorry.
VESPA, which is actually organizing this workshop this week. I will certainly not be complex even in 30 minutes because this activity is so successful, or at least so intense, that it's becoming impossible to talk about everything we've been doing so far in the program in 30 minutes. So I will just give some hints about the activity we have in Europe with a special focus on planetary mapping, of course. So, as you know, VESPA is the name of the work package, of two work packages in a very large European funded program, which is called EuroPlanet 2020. There are a lot of people involved in this single work package, 17 different laboratories, if you count them one by one. Some are groups, especially in France, in CNRS, which is only one partner, and in the observatory of Paris, where there are actually two different laboratories involved. So a total of 12 institute laboratories spread in the observatories, where there are actually two different laboratories. And we also use some contribution from the outside, especially in some activities which are actually sub-networks involving other participants, in particular in spectroscopy. So, okay, what is the basic idea? The problem that we all know in this field is that whenever we want to work with data, we have to look for data, and this is becoming a huge task itself. Simply identifying things that possibly incorrect and typically we have to address many databases, many archive repositories, which all have a specific interface, specific format, procedure, and that's a mess, and we are losing a lot of time doing it. So since we're essentially lazy, one of the ideas was to simplify this problem, this situation as much as possible. We want to work from a single desktop computer, sending one request to many databases, getting the answers in a single or consistent format, and being able, from there, to choose things of interest, in particular by being able to visualize the data themselves, maps as well as the spectra or profiles or dynamic spectra, whatever they are, which means that we need a global system to handle all this. We need a system to issue queries, to receive answers. We need some homogeneity among data formats or some conversion systems. And we need tools to be able to both read and grab the data and possibly start working on it. And from there, we also want to have a possibility to simply pass the selected data of interest that we want to work with in our usual working environment, which can be IDL, NB, whatever, in your case probably GIS. And this is becoming even more tricky because GIS is a full web in itself as far as data formats and data handling are concerned. And this is usually not directly plugged to our planetary science data. So this is a nice dream. It seems to be a very difficult work to do. Has been essentially done already in astronomy in the past 15 years, and this is called the virtual observatory. So the idea of VESPA and previously this activity that Angelo mentioned in the previous program was actually to review what has been developed by the Virtual Observatory in Astronomy and use it for planetary science for all kinds of data, not only observational spaceborne data, of course, but also telescopic images, telescopic measurements, but also including simulations and experimental work in the laboratory, in some places. So this relies on a set of standards, which of course is tuned to handle data in the field of astronomy, and there are big differences with planetary science, but still there is something very common to this, and the idea was to build on the astronomical virtual observatory to reuse their tool, to reuse the standard to describe the data and to access the data. And in fact, we were successful in the previous Europlanet program, which ended 4 years ago. That was called the Europlanet AI. And we actually were able to put together a demonstrator of feasibility of using the Virtual Observatory standard and adapt them to planetary science. Okay, so the current status is in the current program, which started a year and a half ago, which is a big one. VESPA, which is a generic term for all this activity covering essentially 2 different types of activities, which are development and implementation of the system. Altogether represents 25% of the activity of Europlanet, so this is a big thing. This is coordinated by myself, Baptiste in Paris, Angelo in Bremen, and Teresa Castellani. And there are, of course, many important goals. So the main objective in this frame are, first of all, to make more data available, reachable in this system, and this is about half of our activity, to make data available, typically existing archives, existing repositories, and I will say a few words about this. We also need to improve the search interface to find data of interest, and the tools, which are optimized for astronomical data, which are a bit different. And we have also other activities which are important in the long term, building a user community, and this relies on training both the users and the potential data providers. And we need to make it sustainable in the long term, because we don't want this to stop at the end of Europlanet, which is a 4-year program. So how we do this is to pass all standards, the ones that we define, to longer lead consortia, typically the IVOF, which is the consortium in charge of the astronomical VO, but also IPDA, which is the consortium of space agencies to handle planetary science data, and IAU, of course, the international. Then another matter of importance, of course, is to improve the interfaces with other fields, scientific fields, and you could put the border between the VO and the GIS somewhere around here also, because technically it is but this also involves heliophysics, plasma physics, atomic and molecular physics, and so on. So, okay, conceptually this is rather simple. The center of the system is those things which are sets of data sets, services. So this is what you're comfortable with normally, a set of data files in an archive. The only specificity is that on top of this you have some kind of web interface which provides a description of the data and a way to get queries and answers to these queries. So the other piece of importance is what we generally call client, which may be a web interface in which you will enter your query. Say, I want all possible images of Mars in the region of Olympus Mons, but I want specific illumination conditions. I want a part of a specific season in a year, and I'm looking for clouds. So you want typically to have a system, a querying system, which is able to understand this kind of query. And because you're a scientist and you want to ask queries about data in terms that make sense for you scientists, and you don't want to have to endure any Google from computer informatics or whatever. You're interested in things which have a meaning for you, and they are given in terms of coordinates, physical parameters, and so on. So you need this interface, and you want it to be able to send the queries to the data services, and to grab the answers from these data services, and to present you with a list of files or information which are actually matching your query. So, okay, let's assume that this already exists. The next problem will be that you have to find where the data are located, because you don't want to have to search them themselves, and this is another place where we're reciting something which already existed in the video, which is what they call the registry. And this is a catalog of the available services at some point. And each time that somebody implements a new data service, they simply declare it in the registry, and it becomes available to all possible clients. Okay, and it works, and that's it. So since we are reusing what has been defined for astronomy, we're also taking, we're also benefiting from all the other possible pieces, in particular the plotting tools. I will present them in a while. But through these tools, you also have access to the astronomical database, which is of course important because from the start, the planetary science video in this context is directly a part of the astronomical video, and in fact, we successfully convinced astronomers to accept planetary science as a natural extension of the video. But here we have to deal with other pieces, pre-existing ones, in particular the data from the space agencies, which exist on the web, of course, and which, on top of which are accessible through somewhat similar systems. There are access protocols, in particular PDAP, which is a project from IPDS, Consortium of Space Agency, to handle planetary science data. So our VESPA client is actually able to handle this, but this is at a much lesser level of development. So currently it is not extremely efficient. It is implemented both in the PSA ESA and on DARS, which is the Japanese. Okay, so we are using other pieces, and of course, what is of interest for you is this connection probably, which is in a different color here, because it is relying on completely different protocols, and this is really a different one. So, of course, one of our important objectives was to work on this link between the video and the TRS. The beauty of this system is that it is completely open. There is no big data center. You don't have to ask anybody to have your data distributed or making them available. If you want to contribute and if you want to benefit from this infrastructure to distribute your data, the only thing you have to do is to, of course, follow the standard interface. You have to make your data accessible through this protocol, and you have to declare it in the IVOA registry. And it will become immediately visible by all the clients using the registry, and the data themselves will be accessible from any client supporting the access protocols that we are using. So anybody, any small team can contribute to this system by providing more data, and anybody can benefit from this infrastructure to distribute the data and make them visible in the system. Okay, so altogether we are doing nice things, but I'm already late, so I'm cutting this. But okay, an important constraint that we have is from the start we wanted to be very multidisciplinary. We wanted to support every science field in planetary science, and this is a huge work because things are very different. There are already tools, working environments that we want to remain consistent with, but which are restrained to some fields. And of course, for planetary surfaces, GIS are one example of this. Okay. One way we have to keep sustainability in mind, of course. We want to build something solid which lasts longer than the program itself. That is to rely on existing things which are already maintained outside by other consortia. So typically we are relying on the standards provided by each consortia, IPDF, IVOA, IAU mostly, but also SPACE for plasma physics, and of course obviously for the GIS standards. We can have some provide some input for discipline, of course. IPDA, IVOA, IAU are relatively easy to reach. We can discuss with the commission in charge. In fact, we are doing more than this. OGC is a completely different matter, of course. It is an industrial consortium, and the partners are Google, Microsoft, whatever. They don't care a shit about planetary science, of course. And we have absolutely no possibility to send them any message or to ask them to make an exception for us. They don't even listen, so and probably do not even care. So we are. This is a specific interface that we have to use the way it is. So this is an important constraint in this development. I'm just showing how it works. Just to give you an idea, I don't have an internet connection, so I cannot make a demonstration for it, but you should be able to do it on your side. If you're going to this place, this is our main search interface. This is not the only one in VESPA, but this is the one which is really optimized to do. So you're entering your search parameters. You have several panels of search parameters, and most important one are here. You're looking for a target, type or a type of target. You can look for a type of data product, images, etc., profile, whatever. You can look for a type of measurement, which is something a bit unusual in planetary science, but this is a standard stuff in the video. This is why you could say I'm looking for a reflectance spectrum, for instance. And then you're submitting your query, and you will get a results page, because each query from this interface is sent to all the available data services which are present in the record. So you're getting answers from all the data services, and if you go to one data service, you will see the list of files which match your query. So in this case, those are all images on the giant planets. And from there, you can select your preferred data files and send them to plotting tools. So we're using the plotting tools that were developed in the IVOA. They can be used in different ways. You can plot either the metadata, which are typically the location of the measurement. In fact, here those are profiles of Titan from Sears and Cassini. But you can also plot the data themselves. in this case, really the profile, the vertical profile that ICO. And of course, the more data services you have connected, and the more science you can do by simply comparing data of different areas. A typical use case will be, speaking to this Titan example, okay, you're looking for observed vertical profiles in the atmosphere of Titan, so you get a list of results, but you also want to compare this with simulations. So currently this does not exist. We have a service with the vertical profiles, but we don't have the simulations. This is only a piece of software running on the computer. But if it were accessible as a data service from VESPA, in fact, we implemented this use case format, not in Python. You could select the profile of interest for you in the same condition as the observation, compare the two, and check where they agree or where they do not agree. And where they do not agree, of course, you want extra information like seeing maps in this period of the surface by Cassini, and check if there are evaporating lakes or things like that during this period. Okay, so again, this was not implemented for Titan, but we were very close to it for Mars. So someday I will change my example. Okay, how do we develop this during European? We have mostly 4 types of activity: implementing new data, making new data available in the system, improving the existing tools, or developing when there is really nothing to do something that we need, plus training and sustainability. So this is the awful structure explaining how we are working in European. This is complicated. Again, there are 17 partners. But the important thing is that we have 2 big parts: development, implementation. So this is where we are designing what we will be doing, and this is where we are actually doing. And those are structured by thematic fields. So the one of interest for this week are, of course, planetary surfaces, which explicitly includes the link between the real world and the GIS. And of interest also, I think, for this week are small bodies, because it is essentially the same problematic also. And also solid spectroscopy, which is again explicitly included as a science field in VESPA. Simply because there are scattered pieces about spectroscopy of minerals, experimental data, and that are usually difficult to reach. And when you're looking for a typical spectrum of olivine with a certain grain size range, either you know where to find them or you don't. And even if you do, you're probably not aware of the updates of the new data available and so on. So we felt from the start that this is an important field to include in the development. Okay, I'm just describing those 2 things quickly because I'm late. Our goal concerning implementation of new data, making new data available, was to reach a number between 30 and 50 data services program in 4 years, and we actually already reached this objective. But of course, we always want more, so we have 32 data services open and connected right now. At least 10 being designed, that should be ready very soon. We have several ways to implement new data services. VESPA partner are, some of them at least are doing this. But we also have an open call each year when we select 4 to 5 partners, external partners, not in Europlanet. We invite them to a meeting, a 1-week meeting, and help them implement both the data server and service in their institute, and they will be responsible for the data they distribute. But this is on the basis of a science project that they propose. they're telling us, okay, I want to make my data available in this framework, and we are asking them. Okay, so we had the last one 3 weeks ago in Grasse, in Australia, and the next one will be in Prague next year. So if you want to spend a week in Prague, please apply. We also pre-selected 2 big services from the amateur community, pre-selected because those were of particular interesting science quality, one in imaging, one in radio. And of course, we're also accepting spontaneous contribution from these partners. The largest one so far is the PISA with the TSA, which already has an interface on the world TSA. There is an interface. It is not public yet, it is in test. But it's working. The problem that LISA has to face, of course, is to describe the data to the required level of accuracy, and I understand it is very difficult. But this is exactly the same situation as improving the other possible search interfaces. The problem is not with our interface, it is in grabbing the information which is in the PDF description and making it available in general. We also have a close activity with several PDF nodes, in particular small bodies and also in plasma. We have a big common activity with IPDF, but this is what exactly in the steering committee of IPDF. And we have an opportunity to start a direct collaboration with ISO right now, which I'm not commenting because this is working for us. I'm not commenting this either. This is a list of this is our roadmap for data services for the program. So what is in black is already open. What is in blue is being tested, I would say, but some of them are open also. And the red stars are the ones that we opened in the last year. So it gives you an idea of the speed of development of this activity. And the more data there is implemented and available, of course, the more it is attractive for users, but also for data providers, because they want to be able to compare their data with the other one. Tools, and this is something of interest. I'm not going into the details because it is immediately too complicated, but I'm just showing you a first list of the tools that we are using in the video and what they can do for surface science in particular. So Aladdin is always presented as a sky atlas. We consider it usually as an image plotter, an image viewer, a very efficient one, which is able to handle a huge quantity of data at the same time through the internet because it's always communicated and downloading data. Those were our early tries to use Aladdin for planetary surfaces. So this one is ugly, but it is a real mosaic of the moon from smartphone data. Simply the data are not calibrated, so it's not very pretty. But this is actually a mosaic. So from the start, Aladdin had the capacity to make this connecting. And more than that, because you can on Aladdin, and this is 2 years old, from the start you were able to actually use it to plot a list of objects on top of, and all this is in 3 dimensions, of course. You can rotate the sphere. That was Java. We're using other tools. This one's ReadyView has some capacities. It is able mostly to along the spacecraft trajectory, but of course this is more important when you have those sort of cauliflower shaped things that have in plasma data. For surfaces, I'm not sure. Yes, you can do something about. We recently added the possibility to project images on these rotating bodies. This is not really a surface image and cartography, but 3D view is able to handle images. Matisse from the Italian Space Agency is something much more sophisticated in this regard, which is able to really plot data on 3D shape models, including funny ones at 67p, and also taking advantage of the 3D coordinate system, which has to be used in this case because of the concavity. Topcat is a marvelous tool to do almost anything based on tabular data, which can be about anything. I'm skipping the details. It has also some cartography capacity, especially in relation to footprints. This is a coverage of the Verdi data on Rosetta on 67p. So this is only the density of observation, which is plotted here. But this is something which is difficult to do in IDF, for instance, and which is extremely easy to do in Topcat, because Topcat is convolving the number of observations with the size of its marker. So this is very easy to do. So this is a typical case in which you want to do something in IDL or NV, but still communicate with a VO tool which has a specific graphic capabilities that even NV or IDL do not have. And there are, of course, situations of the opposite, where you want to make the computation in Topcat, for instance, especially when you have to cross tables, because Topcat is very, very good at this, and you want to plot the results in IDEA. So the basic idea is that you want to use interfaces between these two domains. We have a specific tool developed for image cubes, and behind this, we also have spectral tools in the VO, most of all Cassis. I haven't mentioned this explicitly, but some of the developers of these tools, Aladdin, Cassis, and 3D, are explicitly funded by VESPA. So we have the capacity to ask them to add extra functions in these tools. The Cassis is an example of such a collaboration, which is very effective, in which we can ask them to support, for instance, reflectance spectra, which is something funny for astronomers, but of course vital to us, but they don't even know what it is. So of course that was not included in any tool, and we are now getting some success in implementing the reflectance data. Okay, so specificities related to surfaces. Je déborde un peu, Mr. Chairman.
We are a bit off, but...
Yeah. But this is important. I should have started.
It's all right.
I'm just stressing things of interest for this for surface. First of all, we want to work with GIS in this field, but we have several modern GIS things. QGIS, I think, is in good shape, but we still have the Planet Server project, which is still in progressive, and that we probably want to be able to use with a VO connection. And Angelo and Pierre have been working, and I've been working a lot in the past year on actually using data services with the VO interface to take advantage of the search capacities of the VO, but to provide some kind of GIS link to the data. So instead of getting the URL of the data file that we can handle in the VO, they have to deal with these WMS or WCF things, which I'm not familiar with, except that they are not what I would be expecting. But they were very successful in providing a close design for this link, in which you can actually address the video data service and handle this kind of links to the data to send them to QGIS or GIS environment and the other way around. So this is of course something that we still want to develop because we only have use cases so far and a system working, of course, but we want to show exactly what are the capacities. And this is very important also for us to tell the VO people that we are doing something unexpected with something that comes from the VO world this time. And that was a problem of importance when dealing with space-borne archives, in particular images. This is an image of Mars, okay, a fake one, but still. And this is the footprint which is classically provided in a PDF, which means that your footprint is essentially empty in general. It's not the definition of an accurate footprint. In the video, there is another way to describe the footprint itself, which is to sample the contour. So there are rules to do that. They develop to define footprints on the sky and to merge them together. So we use this in addition to the bounding box footprint, and this is important because in the data server are implemented functions that are looking for intersects between footprints. So you could, in theory, and in fact it works, look for data which are partially included in this footprint, which is incredibly powerful when you're looking for images or even local data on the planetary surface. It only works on the surface, in fact, not in 3D. We will be trying to extend this a bit, but that will be probably difficult. Currently, this is really a surface-oriented capacity to look for intercept or inclusion between. So we have implemented this already in some data services, and it actually works. And this is something you want to use. Bounding box, so this is previous PBS-like system, but of course the expression footprints are very useful even to define locations of your objects. And the last point I wanted to stress that we will certainly discuss this week is Terraster, which is Finch for that GeoFix, which is some kind of extension of the standard fix format, which is the standard format for astronomical images, to handle planetary surface coordinates, which are a mess for astronomers because we're using many different coordinate systems. They are not rotating in the same direction as one on the sky. And this is really a difficult matter to deal with. But so far we were successful. We also have this technical thing of implementing planetary surface properties inside the astronomical form. But Clara was very successful in this. She only needs 2 extra keywords to do whatever she wants. And this is an example of automated projection. So the interest, of course, is that the VO tools already know how to deal with fits and project everything in real time. So if we can make them understand that, okay, but this is on Mars, you immediately have the matching between the data and the coordinate systems. Just a word on training. We are doing regular action about training. The next one will be next week at EGU. So if you're interested, the session is on Wednesday. You can attend. There are practical sessions in which you are looking at use cases. And concerning standards and data model, we are working on it. Again, Baptiste is really the lead on this, both with IPDA and with IAOL. And we have a lot of documentation materials, anything available
And I will stop here.
Thank you very much. Many thanks, Stefan, for the extended overview. We actually have still 5 minutes of discussion, so the buffer time was handy in this case. If you have any question for Stefan, you still can catch him from now until Friday and next week too. So.
Yes, I have a question. The stock map that you show us that can mark, for example, the coverage of data. Can you also do that for simple spectral data?
Yes, yes, it does work. Topcat is not optimized for spectroscopy, but you can plot whatever graphics you want in Topcat. I think I had an example at some point, which was a profile, and which is essentially the same as a spectrum. You can simply tell him, okay, plot something with this from this table, and you will ask you what kind of plot and what column against what column. So you can very easily get an image of a spectrum, and from there you can probably also rather easily make subtraction, division, but not that much. This is not a spectrum. This is much more.
Any more questions for Stefan? Nobody asks on Open Planetary on Twitter, so I think we can leave for the moment with it. And otherwise, I will then move on to the presentation of Trent on GIS and mapping state of the art. Trent, do you have a HDMI in your? Oh, that's actually pretty cool. Thanks a lot, Stefan. We also have this microphone, but I think you should be able to make it to the big one, as you like. No, you don't need the data point. You have yours.
Yeah.
Okay, cool.
I guess I can use that.
We have to change the. This should work out of the box. Yeah.
Just
Power. Yep.
is that? Is there another way?
The what? This should. Wait. It's on mute. It works. Sorry.
Check.
Yeah, it works good.
Oh, I can speak loud enough, but I guess this is a little bit easier. Should we go for it?
Yeah.
So unfortunately, I'm going to come at this from a very kind of typical USGS mapping planetary view. I don't have. I'm actually excited to be here because of the VO aspects. I'm very naive when it comes to the virtual observatory standards, when it comes to the methods, and so I'm excited to try to learn more. I feel like we've been fighting our own little battle for so long that trying to interop with the VO is going to be hard. It's going to be hard for the not necessarily us technologists, but for the mappers in general. So I'm going to be talking about GIS updates, kind of in general, since we're talking about mapping. But I'll try to touch base on, I guess, what I see as some of the goals that maybe we can tackle here. Okay, so I'd like to really thank Chiara and Angelo for hosting. This kind of came out of nowhere. I think think last year he said we should do a workshop, and magically here we are in a workshop. So that's great. Yeah, without kind of this knowledge or this idea that we need to get together, it wouldn't happen. We are having the planetary data workshop in June, which we're hoping for about 100 to 150 people. Pretty large, and the only reason why it's so large is because we have the mapper meeting at the same time. And the mappers meeting is for geologic mapping specifically. It is covering techniques, the map, the science that they're gaining. It's all over the solar system. So Mars, Europa, VESPA, and I think Ceres. And so there'll be two big sessions. There'll be a session for geologic mapping specifically. And when it comes to those mappers, they don't want to understand OGC. They don't want to understand, you know, what a WMS is. They just want it to work. So this is where I'm coming from my standpoint, from my support is how do we get there for the scientists, not necessarily for the folks in this room. I don't consider myself a scientist, so. The outline for today, I'll talk a tiny bit about what astrogeology is. I kind of already did that. I actually want to point out this kind of new thing, and it actually is very much aligned with the VO goals, this PSDI, planetary data infrastructure. And it's something that we've been doing for years, but we haven't really noticed it. We haven't told NASA what we're doing. And so NASA is pretty much on board. They want to support us. They actually are funding us to do this kind of thing, to support this standardization. And so I want to do a brief introduction to that. I don't really have a connection with the VO yet, so I'll need your help for that. Then I'll have some GIS updates, and I don't think I'm going to have time for that. Let me set my timer, because I have a tendency to go over a lot.
We have the same buffer, so okay. We have some safety net.
Okay. And so the community sensor model is a standard. It's new. It's part of the PSDI. I'm going to try to make it part of the PSDI. I presented it at LPSC, which is a very strange place to present something like a camera sensor model standard. Okay, so what do? I run the Mercator Lab. We're named after not the Mercator projection because we don't like the Mercator projection, but named after the man. But it's also really just an acronym. So I am supported to support geologic mapping. And again, that's why I sort of have this single focus of how do we get GIS to work, because I am supporting geologic mapping as a primary. I'm also trying to support standards and trying to support interoperability. That's a big part of what I fund myself to do, but it really is in support of geologic mapping and mapping in general. So what does astrogeology do? We do a lot of things with standards, and so we do geodesy. So Brent Arkinall is head of the IAA. We also do planetary nomenclature, geologic mapping. And so, again, here's this, not only do we support the mappers, but we support the publication of the GIS template files for USGS and FGDC metadata. So basically the whole gamut from the initialization of the geologic map to the finalization of the publication, which is analogous to kind of what we do with the PDFs. We need to archive it. We need to make it usable. And so that again is where this talk will be coming from. We actually have representation at astrogeology on the PDFs. So archival, documentation, data publication. Something that's new, part of this PSDI, the Planetary Spatial Data Infrastructure, is a group called MapSet. And they actually, at the data workshop, there's a whole afternoon or a whole morning for the MapSet. And MapSet is basically planetary spatial data infrastructure for technology. So we actually have NASA representation as a So let me go back to that. I would like to point out that this is a problem. So OGC is a problem because it is Google, it is Lockheed, it is Boeing, it's a lot of defense and military. So trying to get them to work with planetary data is frustrating, to say the least. I've been going to some of their meetings since probably about 2005, 2006, and it's really hard to get traction. And so the only thing that helps is to make sure that we have people continue to poke them. And so we need more representation. Trying to get people to go there because it's such a kind of a meeting that we don't really, you don't see the gain for maybe 4 or 5 years. So it's very frustrating to go there and have to sit and have to listen to all these presentations and not be able to influence them much. But the only way to influence them is if we have more people representing us. So I did a plenary talk last time, and it felt like it was the first time I had ever been there because half the people were like, "Oh, planetary, that's great, that's neat." And it's like, well, we've been working with you guys for 10 years, but it doesn't feel like it. So it's tough. It's a really tough community to get into because they are focused on GIS, they're focused on data. They're focused, and they actually are spread too thin. They try to do too much. They have a full working body. It takes too long to get standards approved. They work on things like sensor web. They work on things like GML and GIS formats. It's just, they've gone a little too far. They actually are part of this camera sensor model idea too. So it's a very frustrating group to work with. They're slow, just like any standard body, and they're big. So it's hard to break in. Why do I think we need to do that? It's because they do have good standards. Once they actually are implemented, they work for the most part. And so I think we still have to work with them. Some other things that we do work on is GIS format support. GeoTIP is actually from Jet Propulsion Laboratories. It's been around for a long time, and thankfully it's always supported planetary. I don't know how, I think it was just happenstance that it's supported planetary, but we've never had any issue. There's people have implemented it wrong. For example, Socket GXP, we've had to pay them to fix it, but there's plenty of people who have implemented it wrong, but the standard itself works with planetary. And then we also are newly part of this camera sensor model working with. So in general, we have a lot of standards, and you'll notice none of these feature any of the VO standards. And so how are we ever going to get these two? So you guys have done on the NASA side, there's no whatsoever connection between GIS and the VO. And so I think we're going to have to hopefully take the lead from the European side. So history of our GIS, we've been using GIS for about a long time for planetary. In 1994, we actually started to use it for data conversion, simply conversion of geologic maps and topo maps, contour maps, not even DEM, just contour maps. We actually started doing GIS conversions and GIS analysis for geologic maps in 1996, and then quickly kind of progressed into landing site analysis, and then online mapping in 1999, which was really, really hard to do back in the day. And now it's got a lot easier, so that's nice. And of course, I think the reason why we're still using it is because of data overlay and analysis. So just as an introduction, I'm going to try to brief. This is a talk that was given at LPSC. This is a talk that probably will be given at the data workshop. What is PSDI? That's what we're calling what astrogeology is now funded by NASA to do. And so this is the bottom line and this is why we do all this work. The connections with the VO, the connections with OGC, data should just work. And if you work with planetary data, you know it doesn't just work. And this is a quote that I always get from my mappers to say, I just want to drag it in and I just want it to work. And how many times does that actually happen? Not very often. we're getting better at it. If you talked to me 10 years ago, it was more of a nightmare. So it's gotten better. But this is the goal of planetary spatial data infrastructure. And what it is it's basically the construction of the infrastructure to allow data to just work. So this is going to be a very geared towards GIS or spatial data. It's going to be hard to again, to push that limit of how does that work. But why do we need this? We've been doing this, but we needed to put a wrapper around it. We needed to tell NASA, why do we need money for infrastructure? Why are you guys spending so much money on scaffolding? And it's to facilitate standards, but it also, so to define the scaffolding, we actually had to make sure that we identify the themes and the relationship between those themes. I'll get to what those themes are. What we've defined, and it's still new. So, and this is kind of the basis behind the PSDI, is that there's a recognition that data access standards and policies are transient. They come and go. What's not is, what's more important is on the edge. Edge is the data and then the users. I mean, that's why we're here. But, and the thing that wraps all of these things is the technologies. So what makes this hard is that, you know, TopCat, Aladdin, QGIS, ArcMap, they're all going to go away at some point. They're going to be replaced with something better, TopCat 2. And so we have to understand that these interfaces and these ideas and these data access methods are going to change. We used to have to order CD-ROMs. We used to have to go into a lab and look at pictures. Now we just download it. But what facilitates this is that, why do people use this? Is because we hope that NASA will actually implement a policy to say, you need to release the data as such, or with these kind of standards. But again, the data and the users are the most important key, and this middle section changes. We know they change. As we get better internet, it's going to change. So the three things, why are we calling it the spatial data infrastructure? We're calling it because there are hundreds of these that exist. We based ours, we kind of referenced ours based on the US national data infrastructure, but there's international ones for Antarctica, there's ones for Hungary, there's ones for Russia. Lots of countries have these. And in the US, it actually is mandated by the president that we shall do this, but there's 9 foundational data products. And I'm not going to go over all those. And there's 25 ancillary data products. So those are all considered foundational. The 25 ancillary products are things like NDVI, or the vegetation index, or geologic mapping actually falls under ancillary. Foundational is things like hydro and ortho photos. And so when we look at this planetary spatial data infrastructure, only three of the 9 transfer directly, and that's the geodetic reference frame, so the size of the body, the elevation or topography data, and then the orthoimagery or orthoimagery. Those are the only 3 foundational products that transfer directly from the spatial data infrastructure to planetary. Now there's a lot of ancillary ones, but these are the most important things, and these are the ones that we are telling NASA, you need to fund these 3 things as a primary priority. We need to have funding to support the size and shape of the body. We need to have funding to support topography data, and we need to have funding to support nice registered controlled images. So not just an image base, not just something that you throw together, but something that is controlled, registered, bundle adjusted, so that this image becomes a foundation for other images. So this is what we're telling NASA. Okay, you are giving us so many $1 million a year to support this program. We are going to prioritize our data products and our tools and technologies based on these 3 things. And this is still a negotiation. So if there's something we're missing, you'll notice geologic mapping isn't in here, but it is a critical framework. community, we need to make sure these exist for everybody. And so just to kind of put the nail on the head for these three themes, as generated by DLR, here's a nice shape model, foundational data product. Everything needs to align to it. We need to know the size, we need to know the rotation rate. We need to know what north is. There's still battles over what north is for every single body, or the small bodies at least. Elevation and topographic data. This is key for landing site analysis. It's key for understanding again, kind of the size of the body. And to make sure that this topography is registered to the geodetic coordinate frame. We don't really care what the form is, but we need to know that it exists. So if we don't have topography for a body, how do we get it? Topography for Europa, how do we get it? We need to send an instrument to Europa to understand its topography. So that hopefully it not only supports the derived products using existing data, but also can support the generation of new products, or the generation of new missions. And then the last critical data product is we need to have orthorectified images, controlled orthorectified images. And so why do we need that? If your typical kind of GIS 101, you see this road is nice and wavy, and in reality the road is perfectly straight, cut through here, and that's because it hasn't been corrected for topography. So not only do we need to correct the imagery for topography or rectification, we also have to control it together, so that you can build that image pyramid of foundational product, and here's the high-res images that lay on top of it. So just as some use cases, this is for the moon. So we actually have a pretty good system on the moon. We have there's I think 5 laser reflectors, so we have 5 control points on the moon. That's it. Everything else has to be controlled together. Elevation data, we actually have a good set of elevation data from WAC stereo, Kaguya stereo from JAXA, Chandrayaan stereo. So this is a good foundational body. We understand the size and shape of the body. We have the topography, some orthorectification. We actually have the WAC image mosaics, and here's that. So orthorectified ortho mosaics, LRO WAC, some of the allometric VRF. And the only thing that a lot of times we're missing from planetary data is the understanding of the error. And that's a big component of PSEI. Not only do we have to release the data, but we should understand how accurate it is. And currently it's really hard to find that accuracy statements on most of these mosaics. So to follow, I just have some examples of some other foundational. So Messenger has a new image mosaic, and we have a 665 meter DEM generated from actually control points from a bundle adjustment process. It's not from stereo, it's from kind of an iterative solution, so the topography is fairly low res. But I would consider these foundational products. So does that mean we're done with Mercury? We're done up to a certain level of error. And so, of course, as we get better data, we want to have better control of the products. Another good one for Mars is we have the INDEM 2.1, but we also have the Venus IR control mosaics. And these are slowly coming out. They are at 100 meter per pixel. They are bundled, they are controlled together, controlled on top of MOA. They are orthorectified, so that again makes them foundational. Another good set of foundational data products are HRC mosaics and the new DEMs that are coming out. These are orthorectified. They are controlled in MOA. So they up the ante for the resolution. So now we have color and we have higher resolution DEMs. So even if we have a single product, we always want to push and make the next best product. So the Lola Kaguya TC stereo. This is, I have a note on here that why is this maybe not foundational? This is an amazing product from 60 North, 60 South. The problem is that this was kind of these Japanese stereo PDMs were actually kind of worked into place. And so there's quite a bit of error occurred. And so does this make it a foundational product? It's a little hard to tell. It's amazing, and it's gorgeous, and the photography is excellent. But do we need to have a cutoff to say, does this have a stamp of approval from somebody? Who would that be? Who would actually approve a data product as foundational? I don't know. Is it NAPSIT? Is it NASA? We don't really know. But we do have to understand that just because a data product exists doesn't mean it's ready for science. Some other foundational products that are coming out that I've heard of, Pluto and Charon, the New Horizon team will be releasing these soon. Here's the meter per pixel so 315 for Pluto, and the DEM will actually be 315 meters per pixel also. Do I consider these foundational? They're the best things we have. I'm not sure if they are fully bundle adjusted and controlled, but I think they are. And actually, as far as other products being produced, there's the Clementine UV Viz is getting recontrolled by ASU. USGS is funded to do the Europa base map review. There's thoughts, there's kind of rumors out there of a CTX equatorial mosaic. So that's taking 6 to 10 meter image data and actually doing a full bundle adjustment around the equatorial band of Mars. That was going to be a huge project. Phobos. And I'm sure I'm missing some. So if we want to make the slides better, come see me or raise your hand if you have other examples. But I'm trying to gather up all the data that I heard about coming out and want to list those. So as far as transitioning to kind of GIS application support, there's just some really brief updates. So when I talk about GIS applications, you'll notice I'm not talking about Aladdin and TopMap, but I'm talking about things like ArcGIS Pro, which is, I don't know if anybody's used it yet, we still recommend holding on ArcGIS Pro. Global Mapper, and the only reason I support that as a commercial application is because it does have planetary support. It is used heavily by some of the rover folks because it does view sheds and kind of neat things. Maybe the latest version, the people hate or love it, but it has issues because it uses Esri's projection engine, which is a good thing because now Mars is built in, the moon is built in. To the old Indy, don't necessarily like that. Open source GISs, we have our favorite, I think, here is QGIS, but there's others. There's UDIG, Saga, GMT or generic mapping tools, and GRASS, which the only person in the world who I know uses GRASS, right there, Alessandro. So I will say that at least there's GRASS add-ins for QGIS now, so it makes it easier to use. And then also there's a really good suite of plugins for QGIS called Saga from the Saga team. This is an example of QGIS. You can see it. We saw an example of this in Chef on Top. But you know, you have colorization and transparency. So typical things that you want to see in a GIS. The real thing that I want to point out here is not all the numbers and Los Palomas. As far as the version name, the QGIS team does support long-term releases, so you hope that they're stable. But the real thing is this QGIS 3.0, which will have Qt4 and Python 3 support, and that's been a long time coming. Python 3 has been a hard to get over as far as transitioning all the tools to Python 3. Qt4 was also a major problem. We had issues transitioning to Qt4 with ISIS ourselves. So going into ArcMap, I will say that there's been some changes this year. This is my favorite figure. If you turn on every single toolbar in ArcMap, you can see that nobody can use it. And so now you get a geologic mapper in the room and you say, okay, yeah, just use the purple button over here, and they're never going to find it. But so not only do they want the data just to work, they want the tools to be easy. So good luck with that. At 10.5.1, Esri's going to add a couple more bodies. So they actually are going to add VESPA into the interface. They're going to add a series that we are going to push in a Mars sphere. So we've had issues with Mars as an ellipse. If you look at all the data sets that are out there, we can't even agree on the same radius as a community. I will say there's probably about 12 definitions for Mars if you include all the high-rise definitions. So every single 5 degrees, there's a new definition for Mars. So just to make it more complicated for us, we never should have done that. But you know, the HRC team uses a different radius than the USGS, different radius of the MOLA team. It's a mess. And there's not really a way around it, except for the GISs generally just handle it. But eventually, I think as we push these standards, we're trying to push towards a single version. As part of the USGS, I would have to recommend this radius because the IAQ supports it. Esri is supporting servers, so they actually are putting our data on the Amazon S3. We'll probably see that this year. Been working with Lucian Flesha from JPL, and he actually works for Esri now, and a lot of his servers are coming online. We also have support from JPL on tile cache servers with the Mars track and the Moon track services. So those will, I don't know if those are on Amazon S3. I think you guys put them on Amazon too. That's nice because you always have fast access. If it needs to be spawned up in Europe, you can have those services spawned up over there. So what am I saying here? Esri just added planetary support for ArcGIS Online. ArcGIS Online is their online viewer. It's JavaScript. They like to do their viewers in JavaScript now instead of Flash or .NET. Before, none of their interfaces supported planetary. So you would go to the ArcGIS Online, you would set up body, and then the projections and the measurements would be Earth. So you get WGS84. So as of the next release of ArcGIS Online, they will have probably about half a dozen planetary bodies. They focus on Mars, Moon. I think they actually added VESPA. So as far as a training tool for GIS, you don't necessarily have to use an application. You can actually use these free online viewers, and you can have your own data. You can set up classrooms to where everybody has an account and they can upload their own data to a certain extent. But as far as a training tool, ArcGIS Online is great. It's kind of a sandbox for playing around with data, and I do recommend it. It is free until you start adding a lot of data, and we'll try to support that as far as base maps. You can set up crowdsource mechanisms, so you can have people set up a website, and you can have people upload craters. You can do a lot of stuff with that for free. We are attempting to upgrade all of our services, our GIS tile cache. We lost a server last month, so we're going to take that excuse and upgrade to this new version of 10.5. One thing that Esri keeps bugging me about is they want to have PS4 support. So does anybody use PS4 yet? No, but they're interested in adding PS4 support into ArcMap because it's going to take another year for it to get into ArcMap. Before that happens, we have to get PS4 and GDO. So, and I'll explain what GDO is. Some of the things that we do as supporting geologic mapping is we support tool development for ArcMap. We are trying to make concerted efforts that when we write a tool for ArcMap, that it becomes also available in QGIS. So just just a handful of tools. I have a new, Mark Hunter is a new Python guy at USGS, and so this year he's built a few things. Topology checking, which is basically, it sets up a whole environment to say, how well do my polygons look? Do I have any dangles? Do I have to edit anything? How many problems do I have in my geologic map? So that actually sets up and builds a whole table of all your issues. Yes, it actually has a workflow, a loop mechanism to build polygons. RSNAP didn't have a simple way to report well-known text geometries, so we wrote a little tool. You can just click on a polygon and it writes out a well-known text ASCII string for geometries. And then one of the things he just finished, Mark just finished, was this capability to link a lot of cumulative stats. So we call this zonal stats. You take your geologic map, you intersect it with the slopes, and you can get a kind of a sense of which geologic units have higher slopes for landing a rover. And it builds all the cumulative plots into one massive table and one massive chart. So I'm not going to explain how that works, but we'll put those online soon if you're interested in doing slope analysis over rover sites. I always show this slide because these are critical, I think, for planetary support. Tools for graphics and shapes allows you to calculate geodesic areas, lengths, and angles. That should be in your toolbox. We need to port that to ArcGIS Pro. We also probably should make sure that fully functions in QGIS. That way you don't have to worry about what map projection you're in. You calculate these and they give you the right areas, lengths. No map projection supports accurate lengths over all the map. So having these tools that can calculate lengths helps. Geodesic Profiler is something new we're still testing. It basically allows you to do long profiles. Okay.
No, the buffer. We are entering the buffer.
Okay. I have sections, so I can cut it off. Layer tools, and I might maybe get an update. Now that Thomas Neisel he left the community, correct? So he's working for like the CIA or something. I don't know. But he actually has the StrikeIt tool. This is a critical component for geologic maps, especially for high rise. It allows you to calculate the StrikeIt for setting orientation. The one thing that Mark Hunter also wrote for us this year is kind of a tool. We'll call it the slope and aspect test tool. That just allows you to assess whether you feel like Thomas's tool got you the right numbers or the right orientation or the right strike. So we use layer tools a lot. Now that we're mapping on high rise, which is sub-meter pixels, this is a critical component for us to understand units. Something that I want to point out that a lot of people didn't even understand existed. There is a block adjustment tool in ArcMap now. What does that mean? It allows you to take 300 images. It will auto triangulate. It will auto image match, and then you do a least squares fit of the whole adjustment. And so that tool, without that tool, you can't do a foundational product. You can do it in ASIS, you can do it manually, you can do it using Vicker and other software, but ArcMap could not do what I would call a foundational product without that bundle adjustment capability. It's now built in, it's very new. I wouldn't trust it yet, make sure you kind of test it, but it allows you not only to triangulate or bundle adjust across images, it allows you to set up ground control. So you can say this image ties down to this foundational product so that you can build upon that idea that we're building up control images. Okay. So that's something new. I think Envy also has it, but it allowed us to generate about, I don't know, 40 CTX bundle adjusted images very cheaply and in about 200 hours. Now, you're not going to do this for global data sets. That's what ISIS and Bigger are used for. This is for very regional, controlled, bundle adjusted data sets. So this is just some examples of geodesic profiler. This is, we used an Earth example, Grand Canyon. But basically, I can trust that this doesn't have the problem of distortion of the map projection. So this is geodesically calculated. You can finally set vertical exaggerations. Very simple tool, but just so that you know that you're getting good profiles. I know that there's more than one paper that has a very distorted photographic profile. If you're doing very global profiles, you want to make sure you use something that's a little more smart as far as long distance profiles. This is the model adjustment interface. You can see that it has the image ID, how many matches, what intersects it, where you can't really see, but where the control is. You can, if it intersects 4 images, it brings the 4 images, you can move the control point. Very kind of ISIS jigsaw-like, and so interesting interface. And does this mean that all the applications we built over the years go away? No, but this is the right step in the right direction. So I think I'm gonna stop there, and we actually mentioned GDAL a little bit. Let me just, I think most of you probably know, but the reason why GDAL is this, it's just a raster library. All it is just translation formats. It supports probably about 150 formats. And God knows why we have 150 formats. And we keep on adding more, but we do. So now there's PDS4. But you can see that for planetary, you know, we do have support for PDS3, some support. We have support for ISIS 2 and 3, that's the software by USGS. Sebastian added Vigor, and this has been around for a long time, and what I'm here to help, hopefully with a little bit the last couple weeks, the next 2 weeks is to help with GeoFits. It supports GeoTIFF, of course, JPEG, PNG, PDF, bunch of stuff, and there are plans for PDS4. We are going to contract that. And so why do we rely on this so much? Because it is used in ArcMap, it is used in QGIS, it is used in SocketTXT for photography, and it is just used on the command line for Python. So without this tool, we wouldn't have the interoperability we would have for planetary now. It has become kind of a critical thing in my toolbox. And I really made everything kind of come together and work. And it's the back end for WMS. It's a lot of times the back end for WCS. So I can talk about GDAL for forever. But you can see kind of the timeline. 2006, we started adding read support. This year, we just added a writer. And that's interesting because why would we add a writer for this weird format called ISIS? A horrible name, by the way. But why would we add? It's because now we can actually write a GeoTIFF with a ISIS header pointing into the GeoTIFF. So I can support what mappers want, which is a GeoTIFF, and what engineers want. But I can have an ISIS header pointing into the GeoTIFF, and it works. I can have a PDS label pointing into the GeoTIFF. So every single product that I support for download will now be a GeoTIFF with a detached header pointing inside of it, so that I get my interoperability with GeoTIFF, but I also get the planetary label. So all of the products that you'll find posted on astrogeology should eventually be a proper GeoTIFF derived GeoTIFF with ISIS and PDS labels. And then lastly, I'm not going to go into Python, but lastly, GDAL supports all the Python tools we use. So I think that's it. I ran out of time. See here, direct application support. So, thank you. And I'm assuming we're going to talk a lot about this stuff, how to connect. How do we look into the face of a geologic mapper and say that supporting standards is good and fun, supporting the interoperation between VO and OGC is good, because they don't really care. So how do we make it interesting for them to care? Number one, we have to push it, and we have to say, here are the perceived benefits of this. You can find your data easier. You can download your data easier. You don't have to download your data, but also that we have to make sure to push this in terms of ESA, NASA, JAXA, to say, you guys do need to spend money on this stuff, and you guys have already been doing it for a while. But it's important for them to realize that by building these standards and these mechanisms and these tools, we will facilitate science. So I think that's the key, is to continue to say that it will make us more efficient as a community. It will make us, things will start working easier. And as long as they hear that, they're okay and they're willing to fund that. But if we don't continue to push them on this, continue to sell it on, then they might say, why are we spending so much money? Because it does, infrastructure costs a lot. And I think they're starting to realize that. Okay.
Thanks for watching.
Yeah, questions? Oh, and I did. I promised I would put broccoli in my comment. I never got to it, but the current state of ISIS is one giant broccoli thing. And just so you guys know that we are focused on trying to make ISIS better, and hopefully with a new name. But the new goal of ISIS is long term is ISIS as a library, such that you can pull out the flowerets, you can pull out camera, you can pull out the spice that we wrap, you can pull out the data IO, which will hopefully have GDAL included, and you can pull out shape models. So anybody can pull these sections out and use them within their own code. Right now, if you try to use ISIS, it's just this giant. You can't. It's not manageable. It's hard to develop in. We want everything to be wrapped in Python or other languages, Java, so that anybody can use it. So we are working on ISIS. It's going to be a long time, so be patient with us.
I have a broccoli question,
Yes.
Guys, since you mentioned this detached label for ISIS and GeoTIFF on the GDAL side, will ISIS be able also to write those things apart from reading them?
So ISIS can use those directly, 100% compatible. It will currently write
the big
back,
broccoli.
Yeah,
Okay.
Yeah, it will write back into its own format until I can talk them into using GDAL.
Because of course, the possibility will be even massive.
Yeah. So I feel like when I talk about ISIS, I'm from the outside coming in, just like you guys. I work there. I'm not on the team. I'm supporting them in terms of kind of future goals, but I don't work directly with the ISIS programmers. I started to this year. So trying to get them to use GeoTIFF is impossible. Trying to get them to use WMSs or proper OGC calls within the interfaces is really hard. So I'm trying to, by supporting an ISIS writer in GDAL, supporting an ISIS writer in GDAL, I can prove to them to say, here's a GeoTIFF, please start supporting GeoTIFF better.
Then I have another broccoli question.
Yes.
Since we're here and you can deliver it, what about the SPICE kernels that can be mounted in some other web mountable way? Fuse, whatever, WebDAV, FS, NFS, whatever, something that actually can save the users download of half a terabyte of kernels.
So the ISIS team tried to implement that and got about halfway there.
Yeah,
so
because
they did a web service,
yes,
but it's only halfway works. And again, they got funding enough to test it, and then no one's been able to get it funded again. So I think one of the goals of the Planetary Data Workshop, actually hackathon, is to understand how we can start wrapping SPICE better in a web service, whether it's a download service, whether it's an online service, using things like SpicyPy and Community, Python.
I was recalling Andrew's comments on this. Okay.
So it's tough, but that actually might be a hackathon topic at the data workshop, is how do we get SPICE easier to use? not easier to use. It's pretty easy, but how do we get it so it's less painful, so we don't have to download a terabyte?
Yeah. Cool.
All right.
Thanks a lot. Any other question for Trent? Because if that's not the case, we actually keeping up. We're keeping up with the buffer discussion bits, but we still have to eat up the coffee break, and there is some chocolate. Yeah.
Preferably in PDF format.
Yeah, that would be better.
We have Windows 7.
And do you have anything against having your presentation put somewhere linked on the website, like on the wiki? And unpublished data or things that you want to show, whatever. Okay, think about copy when you have better movies here, and then we can bring them. Thanks a lot. There's some chocolate.
You want a PDF file, but then I have a movie, so it has to be PowerPoint. Is that?
Yeah, I guess.
Can I use my own?
Oh yeah, you can actually use your own. It's just for efficiency purpose because it's gonna be 5 minutes, 5 minutes, 5 minutes. So we don't want to waste this time between the talks to set.
Would you be able to do PowerPoint?
But maybe you can also.
Can I give you the PowerPoint?
Yes.
Try to see if the PowerPoint works.
Yeah. But are you trying to launch the video from PowerPoint? Or,
Yeah.
Okay. Because most of the time it doesn't work. So.
Oh really?
Yeah.
But
I mean, you can try. You can try. Let's try. Let's try now. Yeah, you have a USB.
I don't. Can I borrow?
Elle va transférer sa présentation aussi.
Ouais, d'accord. Bon, il faut. I created the folder.
C'est celle de la clé de Chiara. Ok, alors faut voir parce que déjà moi j'étais pas supposé faire. C'est Chiara qui doit le faire.
Non, mais c'est sur ce temps.
Oui. Mais je sais pas. Bon, ok. Je vais faire. On va quand même qu'elle vienne pour.
Même si un dossier
sur le bureau. Je vais couper le stream.